right now we know that a 2.9 magnitude earthquake happened, and the epicenter was in Erie, Colorado.
According to the U.S. Geological Survey, they are reporting that the quake had a magnitude of 2.9.
Across 5 different states, hundreds of thousands of people felt this earthquake.
From above, the endless plains of eastern Colorado and western Kansas present a vision of quiet majesty, an ocean of wheat fields shimmering gold, punctuated by silent clusters of cottonwoods and towns whose main streets haven't changed for generations. To most, this is a region defined by sky and horizon, by the unfurling rhythm of seasons, and by the ancient, steady patience of the land itself. It is not a place given to drama, not a place, most would say, where the earth itself seems likely to move. But along this storied border in 2025, something truly extraordinary is under investigation. Beneath the swaying grasslands and the shallow roots of a recovering landscape, scientists have detected a geologic anomaly, a subtle but intriguing shift in the Earth's crust. What began as the faintest tremor, lost in the planet's ceaseless background hum, is now emerging as an event that could reshape scientific understanding of America's heartland. This isn't an earthquake in the way we imagine on the Pacific coast, nor does it echo with the grandeur of mountain building along the Rockies. Instead, the land here may be sagging ever so slightly, as if the very bones of the North American continent are adjusting, one deep and almost imperceptible breath at a time. Sophisticated instruments, satellite radar, high-precision GPS stations, and deep subsurface monitors are focusing on a consistent trend. The crust along the Colorado-Kansas border is in motion, perhaps more than previously thought. In geologic terms, it is not a sudden rupture, but rather a drip in which ancient slabs of rock may be slowly peeling away beneath the continental surface and moving deeper into the mantle below. How could this occur in the heart of what has long been considered a stable continent? What exactly is motivating this deep, silent disturbance? And, perhaps most importantly, what does it mean for the stability and future of the land above? The Dripping Craton. Geologists have long spoken of cratons, those dense, ancient segments of continental crust that form the backbone of continents, generally thought of as immovable and unimaginably old. These relics have anchored North America for billions of years, resisting the restlessness experienced elsewhere, where mountains rise and oceans spread. Yet, beneath the borderlands of Colorado and Kansas, this bedrock may be changing in unexpected ways. Recent studies have been made possible, in part, by the unexpectedly beneficial rains of 2025, which allowed scientists to more easily deploy sensitive instruments on softened ground. Drawing on satellite surveys, borehole tilt meters, and seismic sensors, researchers are assembling a detailed picture. There may be kilometer-scale volumes of lower crust slowly detaching, a process sometimes called crustal dripping. This isn't like a landslide or fault movement at the surface. Instead, it's as if a great ancient sheet of rock, heated by the depths of the earth and pressed by millennia of tectonic pressure, becomes so dense in places that it can no longer stay afloat atop the softer upper mantle. These dense parts may slowly sink, making room above and leaving the uppermost crust to sag in response. The signs are subtle but cumulative. Gravitational field anomalies, small magnetic variations, and changes in heat flow point to internal movement. Seismic waves slow as they pass through the area, suggesting pockets of altered rock or localized partial melting. In some zones, satellite radar interferometry, INSAR, shows surface depression patterns consistent with crustal loss deep below. This process is incredibly slow and silent, visible only through the most sensitive instruments. The plains are sinking by millimeters over months or years, far beyond what can be noticed by those living on the land, but clear in the mathematical models of modern geodesy. What's striking is how crustal dripping was once a hypothetical, predicted by models of gravitational instability, but rarely documented outside active tectonic belts. For it to occur beneath the relatively stable North American craton suggests a deeper, dynamic history, one in which even the most ancient structures are not immune to change. Could this slow-motion descent influence groundwater systems, or affect the way energy and minerals are stored and accessed? If cratons, once thought to be permanent fixtures, are indeed susceptible to internal collapse, then the landscape, ecosystems, and human settlements built upon them may need to be reconsidered in a new geodynamic light. And if it's happening here, where else might Earth's most stable foundations be quietly falling away? The Telltale Sag. It was not a catastrophic event or a visible crack that first drew scientific attention to the Colorado-Kansas region, but rather minor anomalies in long-term data, newly established high-precision GPS monitoring networks, installed after years of drought and recovery as part of efforts to better understand water-related subsidence, began to detect a regional trend. Over a broad area, the ground was gently sinking. The pattern was not random. The subtle sag stretched along a defined, asymmetric zone, deepening and spreading over several months. Satellite radar imagery, specifically interferometric synthetic aperture radar, INSAR, confirmed these measurements, showing minor downward vertical displacements that were not easily explained by seasonal changes, aquifer drawdown, or agricultural overuse. Geological modeling added another layer of intrigue. When the subsidence data were mapped in 3 dimensions, a deeper story emerged. The crust in this area appears to be slowly flexing downward in a broad arc, suggesting the presence of an incipient crustal drip, a volume of denser, older rock possibly detaching under its own weight. This hypothesis aligns with global models of delamination, a process where dense lower crust detaches and sinks into the mantle, triggering surface subsidence and potentially drawing hotter material upward to fill the void. For the people living and working above, the effects remain subtle. A slightly deeper ditch, a shifting foundation, a change in the water table. But to geologists, these are the fingerprints of a deeper dynamism. This region, long considered part of North America's stable interior, may in fact be undergoing slow internal restructuring. This raises new questions about the role of climate variation. In particular, how does the region's strong drought gradient interact with its crustal evolution? Northern Colorado, in recent years, has seen sharp boundaries between prolonged drought and sudden rainfall, sometimes separated by just a few miles. Such abrupt transitions dramatically alter soil load, groundwater pressure, and pore fluid migration. Could fluctuations in moisture levels act as a trigger or amplifier of crustal responses, or do they simply overlay a deeper tectonic mechanism already at work? Some geophysicists now speculate that repeated wet-dry cycling in the upper crust could act as a catalyst, shifting weight, weakening boundaries, or facilitating microfractures that gradually transmit stress to deeper layers. In this scenario, surface conditions become not just a variable, but a co-conspirator, interacting with deep Earth processes over timescales longer than any storm cycle or planting season. Ultimately, the sinking plains of Colorado and Kansas represent more than geological curiosity. They are a case study in interconnectedness, where the sky, the soil, and the mantle below may all speak the same quiet language of change. Heat rising from below. As surface instruments measured the slow descent of the plains, researchers naturally wondered if other signals, like heat or gas emissions, might accompany the crustal movement. Subtle temperature changes, after all, often precede or accompany crustal flexure, providing clues to processes that can't be seen, but may be felt through indirect evidence. To investigate, teams deployed thermal drones, infrared imaging arrays, and shallow borehole temperature probes cross a grid spanning several counties. These surveys mapped energy fluxes invisible to the naked eye, but detectable with modern instrumentation. In certain locations, slight increases in ground temperature were recorded, typically just 0.5 to 1.2 degrees Fahrenheit above long-term seasonal averages. While modest, these anomalies appeared consistent and localized, clustering in areas already marked by ground subsidence. In tandem, soil gas sensors installed near fault traces and suspected subsurface weaknesses began detecting faint but persistent emissions of carbon dioxide and hydrogen sulfide, both common in areas where deep fluids rise from warmer geological layers. Though the concentrations were far below hazardous levels, their presence hinted at fluid migration from deeper zones, possibly released by the sagging crust, and increased permeability in certain rock layers. Intrigued by these signs, scientists turned to magnetotelluric (MT) imaging, a powerful method for mapping the electrical resistivity of rocks many kilometers below the surface. The MT results revealed broad zones of mild conductivity, not suggestive of large magma bodies, but consistent with brines, partially melted rocks, or fluid-saturated fractures. These zones often correlated with surface depressions, suggesting a coupling between surface deformation and deeper crustal behavior. What does this mean? While there is no evidence of a geothermal hotspot or volcanic system in the classic sense, the increased conductivity, thermal gradients, and gas emissions may all point to a subtle shift in the regional geothermal regime. These findings have begun to shift how scientists view even stable parts of North America. Places once assumed to be geologically inactive now reveal quiet, persistent transformations. Moreover, this possible geothermal signal, however faint, could be a key factor in groundwater movement, soil mineral changes, or even microbial activity in deeper layers. Some researchers are now investigating whether microseismic swarms, previously written off as noise, may reflect crustal stress changes linked to fluid pressure variations at depth. The implications are both scientific and practical. If slow geothermal shifts are occurring beneath America's breadbasket, they could influence soil chemistry, infrastructure planning, and long-term water availability. For now, the crust beneath eastern Colorado and western Kansas whispers rather than shouts, but those whispers are being heard. Microearthquakes, a silent alarm. Even minor shifts in the deep crust can produce vibrations, microearthquakes, felt only by sensitive seismometers. In recent years, networks of seismic arrays have been deployed across northern Colorado and Kansas, partly to monitor unusual subsidence, and partly to track the subtle tremors associated with both natural processes and human activity. The data reveal clusters of microearthquakes, most undetectable without specialized equipment. These quakes, occurring at depths of 10 to 30 kilometers, seem to concentrate beneath the area where the surface sag is most pronounced. Interestingly, there is some evidence that these microquakes spike after heavy precipitation, suggesting a possible connection between the loading or unloading of groundwater above and the movement of rocks below. The character of these quakes is telling. They tend to repeat in the same locations, forming patterns that geologists call repeaters. This regularity might signal regions of continued stress relief as the crust decompresses and adjusts to deep-seated change, whether by dripping, bending, or simply rearranging its internal grains. Whether these tremors are warnings of a greater rearrangement or simply the normal soundtrack of slow geologic change is an open question. What is certain is that they point to an environment slowly shifting for reasons that science continues to probe. Minerals and the ghosts of deep time. Whenever the deep crust shifts, it leaves traces in the minerals brought to the surface. Core samples drilled for mineral exploration in the Colorado-Kansas region, pursuing resources like silicon, sulfur, talc, tellurium, and others, have recently revealed unexpected patterns. Some samples display bands rich in zeolites and glassy volcanic relics, evidence of old hydrothermal processes. In addition, transformations of clay minerals, such as smectite converting to elite, have been observed, typically a sign of elevated temperatures at depth. In small but notable spikes, elements such as boron, sulfur, tantalum, and tellurium become more concentrated, suggesting movement of deep fluids through the crust. Of particular scientific interest are isotopic anomalies, subtle variations in oxygen and hydrogen that signal water rock interactions taking place far beneath the surface at temperatures much higher than normal groundwater interactions would produce. These variations mirror those found in geothermal regions with active crustal processes, raising fresh questions about the nature and extent of change happening deep below. Could these mineralogical clues represent the fingerprints of a world in transformation? Are we witnessing the lingering effects of ancient volcanic activity, or are new processes quietly rewriting the underground landscape right now? These are questions geologists hope to answer as research continues. A land strained at the seams. The border between Colorado and Kansas is marked as much by hidden geology as by rivers or roads. To the west, the Rockies rise. To the east, broad prairies stretch for miles. Beneath the surface, equally dramatic boundaries exist. The collision of stable craton with the more active western region, mapped by faults, fractures, and sediment-filled basins. Recent advances in geodetic imaging and fault analysis now indicate that this region sits at a technical intersection, the margin between the extending western United States, known as the Basin and Range, and the ancient continental core. The interaction of these two zones may be playing a role in the observed crustal sag, allowing stresses to manifest not in obvious earthquakes, but in subtle creeping deformation and the gentle descent of large segments of the lower crust. The land above may already be responding. Satellite imagery shows modest warping of certain surface features and altered drainage paths after episodes of heavy rainfall. These changes are gradual, unlikely to alarm most residents, but fascinating to earth scientists intent on unraveling the region's geologic story. Perhaps most intriguing are the ancient faults, mapped in drilling logs and chemical signatures, which could offer pathways for deep crust to descend or for fluids to ascend. Their presence hints at the interconnectedness of forces hundreds of millions of years old, with events unfolding in 2025. Economic and environmental ripples. All of these developments are more than scientific curiosities. They affect the people and economies above ground as well. In 2025, beneficial rainfall of 1 to 3 inches finally relieved sections of eastern Colorado and Kansas from moderate to severe drought, leading to the first noticeable improvements in years. Ranchers and farmers welcomed the shift, hopeful for a return to reliable harvests and replenished water supplies. Yet, for those paying attention to the crustal movements below, the optimism is tinged with caution. Those involved in mining and mineral resource extraction, seeking silicon, silver, sulfur, talc, tellurium, tantalum, and related materials, will need to monitor subsurface changes closely. Crustal sag and mineralogical changes can affect the availability of economically valuable deposits, shifting the viability of some mines while perhaps exposing new opportunities in others. There are environmental risks as well. Subtle crustal movements can reroute groundwater flows, just as rains restored depleted aquifers, risking local shortages or contamination. Migration of gases like carbon dioxide and hydrogen sulfide, though currently only minor, poses a risk if fracture patterns shift further. The region's reliance on groundwater for communities, farming, and ranching makes any disruption a source of concern. Even changes that seem unrelated, such as slight variations in the taste of tap water or new sediment in previously clear springs, may be tied to deep geologic change. The need for ongoing monitoring, scientific transparency, and careful management is clear as all these factors interact. A moment of scientific urgency. The investigation into crustal behavior in Colorado and Kansas is a rare opportunity for science to witness deep earth dynamics at a traditionally stable site. It has united seismologists, geochemists, hydrologists, and geodesists, pooling resources and expertise to better understand both the processes underway and their potential effects. Sophisticated technology is at the forefront. Satellite interferometry, deep seismic stations, ground-based and airborne sensors, and real-time groundwater measurements. As data streams in, researchers strive to unravel whether this phenomenon is unique or merely the first documented case of a wider, long-term cycle affecting continental interiors. For local governments and residents, new advisory panels and town meetings are becoming a part of the landscape. Many recognize that climate-driven extremes, such as severe droughts followed by unusually heavy rains, can amplify the consequences of subsurface changes. Policymakers are faced with questions that defy easy answers. How do you prepare for a danger measured in millimeters, unfolding in the silence beneath your feet? This is a time of both scientific excitement and real-world uncertainty. Understanding these processes could advance our knowledge of the continent's mechanical behavior, but it also invites us to confront risks we never anticipated. On shifting ground. As summer deepens across the plains of Colorado and Kansas, evidence continues to accumulate. The combination of beneficial rains, subtle shifts in the landscape, gentle heat anomalies, and clusters of tiny earthquakes tell a story both ancient and new. Overhead, satellites observe every hint of movement, every subtle signal that the land, seemingly so timeless, remains responsive to forces within. Below, analysis of minerals and seismic waves reveal a world in careful, gradual motion. In research labs, scientists debate the meaning of each new measurement, striving to forecast what comes next. The Earth keeps its secrets well. For now, there are no alarms or headlines, only a quiet realization that the ground itself, from which lives and histories are built, is changing in ways not seen before. What the future holds remains an open question. Is this merely the last ripple of ancient tectonic tides, destined to fade back into stability? Or is it the first act of a transformation that will play out over centuries, reshaping the landscape, the water, and the very story of America's heartland? We may not have all the answers, but we know this: the land beneath our feet, however steadfast it may appear, is never truly still. Stay curious, stay informed, and keep your eyes on the horizon, because the ground beneath your feet may yet surprise you. Like this video if you want the latest on Earth's hidden movements. Subscribe to follow new discoveries from beneath the crust, and let us know in the comments, is this the start of a continental transformation or another mystery waiting centuries to unfold? Thank you for watching, and remember, on the quietest plains in America, the Earth is never truly still.